Okay, I guess you guys can hear me, right? So not a lot of you guys here yet. So I guess during the weekend I'm not sure like you guys uh kind of came with the same. I'm not sure it's problem, but it's kind of a security fix, I guess, from the university. It seems that like um all of us when you connect to Zoom, you need to like key in the password. So I hope that like you guys didn't have any trouble looking for the passwords in the email. But it's not like I like to have the password. It's like the university require. Basically, I cannot do anything. So it's just suddenly that I find out the Zoom connection you need password for that. Um, and so I don't know. I cannot hear anything from you guys. Let me see if I can see any chat or something. Um, I see there's a little bit more. See if I chat. How can I see chat? I'm still quite confused. Oh, here. Okay, no one say anything. I guess it's okay. So I changed my mind over the last week and weekend. Is I was thinking like to first talk about the camera models and then like stereo view, stereo vision. Um, but then I don't know. I see many of you guys like for the final project like to do something about deep learning. So or like for the last several times I just push it to the near end. Like so I think it kind of makes sense because it's like the last things. But this time I just want to um, kind of like talk about this earlier. So so most likely I will talk about the CAM models. It's kind of weird, but it's a computer vision course. But I will talk about CAM models in the last week. So, but that's the plan basically. So okay, we'll talk about deep learning. So um, and I guess many of you already heard of that. Like probably most of you had heard of that. Uh, and it's basically it's I shouldn't say it's nothing, but it's really some not exactly very new stuff, but it's a fancy word or like a sassy word for like neural networks, and but of course if you look at like research right now, this is kind of old Apple slides from folks in Stanford, and but it's still true nowadays. Like you go to conferences, like still most of the papers are kind of like a little bit will be kind of like maybe 80% or mm, maybe more or less is related to like neural networks. So and a big reason is that it really works. So we'll look into that like, but I actually quite contrary to many of people think. Oh, it's really kind of like new and cutting edge or something like that. But honestly, many of these ideas is pretty simple and it's actually even simpler than some of the stuff that we can look into. For example, like um, yeah, you'll see about that. So and I just a one page summary that my understanding of deep learning. So it's the name suggests as the name suggests is like you have a kind of hierarchical structure of learning. So it's deep. It's like you have like many layers. So deep in the sense that you have layers of learning. So you will see more about that. And we have this so-called end-to-end, and you will see more about that also. Like why we call it end-to-end. It's something like oh, I should just give you a quick overview. It's like um, for for in the past, like when we say learning, so maybe I should go more detailed machine learning later on. But for example, if I want to recognize something in a scene, for example, I want to recognize a cat. So the classic approach would be like, okay, we would like to first, like, from the scene, try to extract some features, for example, some edge features, like some line shape, uh, etc., whatever. And then from those features, I I I will get a lot of data. And first, actually I missed that. First I should get a lot of data, and for all these images in the data set, I will just extract the same features. And then, of course, I have the labels. Labels will be the ground truth. I know, okay, this image is a cat, this image is not a cat, and so on. And then, like, I will try to build a classifier. A so-called classifier is just something that you can train, a model you can train, so that, like, when you input the features into the classifier, it will just spit out the output, basically spit out a label, whether it's a cat or dog and so on. So in the past, we have this kind of model. For example, very popular model would be like support vector machine. So we have designed some features like Hertz corner detector, edge features, and so on, all of them put into the model, uh, and then, like, we'll train this model, and then, like, the model will able to classify cat, dog, and so on. So now end to end in the sense is like we even skip the part that we are going to engineering uh, the features. So we're not going to, like, kind of like humanly, I mean by human, trying to decide like what kind of features is good or bad. But uh, in contrast, we will just have the data, like raw data. So in this case, like raw images, and then I just plug into our model, and we have the output labels there. I'm just trying to train everything automatically. So and as you see, like, this is like a very small set of tools or like simple idea that actually can solve many problems. It's not all problems, but lots of problems, as long as data are available. And so therefore you can see that there's led to like many rapid progress in on many different kind of like sub problems. For example, like in segmentations and uh, or lots of other stuff, uh, mostly like recognition. And it's very loosely inspired by the brain, like, or like the neural system. um, so okay, and if you this is an introduction. Like, I don't know how far I will go. Maybe I will take more than one class for this. Actually, I think I will take more than one class for this. uh, and uh, and for more in depth, like, but you can try to take my other class as well. Actually, it's in parallel this semester. It's a neural network class. The name is artificial neural networks, but it's really talking about deep learning, all aspects of the deep learning. And so it will offer again a probably next spring if you're interested. Like, it's a graduate class, you can register for that. Um, and So first of all, like, why people get so interested? So you look at this problem, like, it's very popular, was very popular several years ago. Like, this is a slide in 2014. Like, this is called this image lag challenge. So you have like 1,000 classes. For example, you have like object here, like I have an image. You have kind of like a particular like object inside the image, just one object typically. So for example, like here there's some potential labels, like for this, or to describe this object. For example, a steel drum. Of course, this can be a boy here or something like that. I don't know what kind of object class, or do they have a boy there? Maybe, I don't know. So, but anyway, like, so the challenge is that you have lots of these images, a million images, and have like 1,000 classes. You just want to recognize that. So this is the training image available for you. So it's given to you um, for building the model, and then you just try to have a new image to recognize whether it's belong to one of these thousand classes, and typically like you have the um, you have the leeway to say, okay, I just think the top five possible objects in the scene is like these five. If I get correct in one of these five, I would say it's correct. For example, here in this case, it's steel drums. I also classify something like T-shirt and drumstick and so on. But since I have steel drum here, so I consider this one as correct classification. So if for this one, if this is a steel drum instead of a giant panda, so it's not a correct classification. So it was a pretty challenging problem, and for a long period of time. Actually, if you can see, like even for a decade ago, not too long ago, before deep learning getting popularized. So just a decade ago, like 2010, is still using these classic approaches. So we trying to extract classic features. For example, HOG, we didn't talk about HOG. I think we talked about FBP, I forgot. So different kind of features, and then like, oh, we talk about HOG, right? Yeah, we talk about HOG. And then like, and then we kind of do some coding into some long vector, then like, eventually like do some polling, will be like kind of like sampling, just remove some of this just to compress the feature a little bit, and then like eventually do SVM, that support vector machine, and train that. And this is the winner for 2010, basically. That's the model by UIUC and NEC. And then like this is like basically 2012 is the year that deep learning goes into the area of computer vision. And actually kind of begin the conquest, is that the word, to entire basically technological field. And so this is by the Hinton's group, Jeffrey Hinton's group. He's considered like the kind of like the father of deep learning, and we'll see more about that. And then later on, like there's a Google Lab, VGG Lab. It's like different kind of neural network architecture. And that's 2015. That's by Microsoft Research Asia. This is like kind of so-called West Lab. We may talk more about it later, but I today I will for technically I will focus more on neural network, very general neural network, and we will look into this backpropagation algorithm in more detail, and that's the plan basically. So you can see like this is the challenge again, like in the result of the challenge image-like classification for the top 5% error rate. So in 2010, that I just mentioned, this NEC UIUC work, like the winner there is like near 30% like error rate, but you see like it dropped like quickly, and actually the gap here from 2011 and 2012, you see the big gap. Before that, it's like a slight gap, right? Big, or before that, it's like not. It's also called like shallow model. So it's like hand engineering features, and this suddenly like we're trying to let the machine to do everything, like not just trying to train the classifier, but also like let in decide the features as well. So we can see a big gap, kind of like big drop in terms of the error rate, and then afterward we continue to improve. Like all this now is like based on neural networks, and after 2015, like this is not considered as a challenging problem anymore. So like people move on to like other problems basically, and yeah, this is just for fun. Like that's one researcher, like Andrew Karpathy. He tried to see like how good he is. Like this is kind of painful, there's 1,000 classes. So he manually tried to look at each of them and try to recognize what class is supposed to be. And of course, like, because 1,000 classes, he cannot remember the label. So he need to go back and forth. I don't know how he do it. But he tried to did that like and spent like 2 weeks for that like as a PhD student just for fun, and then like he did like 5%. So it's like in 2015 already like in this sense like just pure like this kind of magic, the computer is already doing better than human. But of course, this is controversial because this is only one person, and of course, um, you will see later on like there's this kind of model is not perfect. That's like still in many sense like human is doing better, like even for the recognition problem, in some dimension. So we will go into that. Maybe if I don't remember, you can ask me again. I forgot to mention that. Yeah. So and as I mentioned, the recognition problem become like not so kind of challenging anymore. So people look into more difficult problem. For example, like instead of an image or a scene only have one object, we want to look at like a scene with a more complex semantic. So you have like multiple objects here, and also we want to be able to identify like each of the object and kind of localize them. So this is known as an object detection problem. So you see there's a car here, so you just draw a bounding box there and say, okay, it's here, and I am so confident like here is like the probability of confidence that like oh this is a to me is a 100% sure this is a car and something like that. This is like 99.7% I think is a dog and so on. And for the detection problem, the trend is similar. So you can see that like this is before deep learning, and then after like people using like deep learning approaches, it just have a sudden jump. Like basically in 2011 and 2012, it's almost like there's no gain here. So you have a very little gain, and afterwards it just came the progress is really quick. And again, like I didn't have the plot like for later years. You just nowadays again you don't consider this a really difficult problem anymore. Although like to kind of detect all the objects real time is still kind of can be expensive depending on what kind of hardware you're using. Of course, if you have you use a Tesla and like basically like they can have object detection. It's like everything is implemented on the FPGA, then it will be a different story. So and this is another illustration problem for like object segmentation. This is pretty nice result, but there's work that is even better. I'm not showing here. The latest work is that you can segment so well it's almost like the ground truth basically. And using similar idea, you can do have like pose estimation as well. Just look at the picture, you can kind of detect the pose of each of the human here. And you can also have some fun with image captioning, like based on whatever image you're looking at, like you can build a model just to spit out like okay what was that, describe, have a description of that image, that image, that scene. So for example, like for this one, a man in black shirt is playing guitar. This is a rather old like result already. That's I think I didn't update it. The latest one probably is more impressive. And that sometimes is correct. Like okay, here is all the correct results here. You have a girl in pink dress is jumping in air, and a black and white dog jumps over bar. Like it's quite accurate. And we can also have this kind of dense image captioning. Is similar to like what we had earlier, but it's kind of like have a higher resolution, similar to like from an analogy from recognition to object detection. This is like from image captioning to like dense image captioning. You on the entire scene, you're trying to describe all of the what's happening in the scene here. And we even can have like this kind of visual question answering. It's like I think it's still like rather challenging. So that you have an image here, then you can ask a question and see like if you can answer this correctly. So for example, like this is like this image, right, who is behind the batter. So we need to say it's like the catcher. So this is a multiple choice question here still. So you have some things you can to choose. So uh, and yeah, this has like kind of similar stuff here. So it just show like some of this wrong answer here anyway. Um, and you can also like combine this deep learning like to this more low level class image processing problem. For example, like this supervised solution. So uh, I mean, you remember like we do like have bicubic like upsampling. We mentioned that like, and nowadays if you use like deep learning approaches, you can get much better result like this one. And you can also generate art. So this is like some work that's pretty interesting. I'm not sure I'm going to talk about this. Like, you guys let me know. Like, if you like to hear more about it, I may talk about that. Like, so maybe just for this one, this I think this is fun. So basically, like what you have is like you see like this have like image of different styles, right? For example, these are different images from different artists. Like they have different styles, right? So you try to kind of combine like style with the image content. For example, this is the original image, is a photo here, and then like I from like different artists, I can learn the styles of those artists, and then I can apply the style to this original image to create like an image of different styles. So and and yeah, and that's something. Actually, it's as I said, like, it's a conquest, not just to computer vision, it's to everywhere. So, for example, like, I guess the next arena that like deep learning is really doing really well and actually conquer the entire field is like natural language processing. So nowadays, like basically, if you use Google Translate or like use all kind of like synthetic, for example, text to speech to, sorry, text to speech, or like the other way around, like uh, voice to text, like all these techniques now is all based on deep learning. So just several years ago, like it's all based on something else, like, and now it's like all based on deep learning. And so I mean, of course, we won't go into this one at all because this is not a language processing class here. So and also, I guess you heard of that also, like a couple years ago, people talking about, wow, like AI is pretty amazing now. It can like beat people in terms of Go. Like several years ago, like people thought that Go is like unbeatable as a game for computer. So it thought that like it needs lots of like some kind of deep insight or something like that. But I guess it turns out like uh, we as human, it tends to overweight ourselves a lot. So and it's just like if you look at AlphaGo, like it has a little bit new idea. For example, using CNN on that, like, but after all, it's not so different from like what we have that a like Deep Blue at that time uh, beat the world champion in terms of yeah, in the game of chess. So yeah, but anyway, so and besides like Go, like we can also let the build deep learning model like to play games. For example, like this, like playing Atari games. Actually that's more I guess probably you guys heard of that. Like for example, AlphaStar, or like this is like also from DeepMind that is trying to that basically build AlphaGo, also trying to build a kind of artificial game player to play StarCraft and then like beat the world champion teams or something like lots of other similar kind of I guess like try to like kind of build deep learning models to play different games and so that's okay. It's so quiet. I see if I see. Let me check with chat again. Just have this. Okay. I don't know. Sometimes last couple of times I didn't check with chat. I see like so many people chatting. Like this time just okay. So any questions or comments? I just want to hear your voice. Uh
Dr. Chief, I have a question.
yes.
My project proposal, I need to do a little bit of face recognition if I get to the end. Can I do that without, no, I'm sorry, not recognition, just detection? Can I do that without neural networking? Can I just do that with normal image processing? Or do I need to try to convert my project to a neural network?
Is uh I actually, I would suggest you try it out. If you have other components, I mean, I'm kind of against you guys that okay, just grab a uh, open source and do not understand everything and just run it and submit as project. But if you have other components and then like you need that piece and just to compete a kind of like have a more value of your project, I'm totally for that. So and it will take a little bit time, but for some of these open source, for example, YOLO, like it's quite well uh, I won't say documented, but in the sense that if you just want to get it one, it's like a couple hours. So you go download that, and then if you just use the pre-trained model, it's basically one from like you don't need to modify anything. So I will actually encourage you guys at least go take a look, but it's not mandatory. Yeah. So any other questions or comments? Um, so if not, I guess what I'm going to do is uh, I think because it's kind of new, at least I like to give a very quick overview of kind of like some kind of machine learning idea. Although I already mentioned some of those um, earlier. So, but the I guess the uh, I'm looking for the English word again. But anyway, the why we have this kind of learning idea to solve problem is that like using classic approach. For example, if you think of like what we mean by algorithm. For example, we have a problems, so we start with like in the Asian age, maybe like we just try to tackle something like with every time I think of a new idea or something like that. Uh, but eventually find that there's some pattern that we can solve the same problem with using the same kind of like procedures. So eventually we develop some of these kind of algorithms. For example, like the classic problems, like it would be sorting. Right? If you have something like sorting a list like that, we know that we can do something like bubble sort, or like it won't be very efficient, but we know okay we do this same kind of along this line of procedure, we can always able to solve this type of problem. But there are problems that is like it's very difficult to design algorithms to solve that. Like this classic problem would be like object recognition. You have an image here. Okay, we say okay, given this image, I like to write a function to say okay whether this image is an apple or like a tomato or a cow. So it I don't think anyone will have any idea where to get started. So how do I kind of recognize an apple? So should I try to what? I don't even know how to get started. Maybe I find some address and then okay I guess mm, yeah just doesn't look like there's any way we can do it like reasonably. And of course like people try in the past but it doesn't make seems to be make any sense because I from different views just like have like totally kind of like the same. For example, we mentioned a chair like in the past, right? Just for oh, okay, sorry, I get confused. I mentioned that in other class. For example, we try to recognize chair, but chair can be like, I mean, it can look totally different, but semantically, as long as we can sit on, like we would say, is a chair, right? So we have many objects will be like that, and even like for something like dog, cats, maybe they are more well defined, I would say, but based on like how they pose themselves, like it looks very different to us, right? So therefore, like we have this data-driven approach. What we are going to do is like we will gather like sample examples of this cat, cats, dogs, marks, and so on. Then based on this example, we're just trying to train our model such that like we're going to able to predict whether it's a cat or dog. So this is like I mentioned earlier. So the classic approach is we're going to extract features, so any kind of features, and then we're going to train this kind of model, this classifier. So wait. Uh, yeah, using this training label, so we train the classifier. So we have a learn classifier here, and then this classifier can be like, for example, support vector machine. And then during testing, we will try to extract same kind of features from the test image, and then from the learn classifier, we'll speed out the prediction. And this is the basically supervised learning. So supervised in the sense that I gave you the exact label what you're seeing. So I tell you this is an apple, this is a cat, this is a dog, and so on. So and more precisely, now what we have like what we are trying to train, you can think of is really something like this. We have this is your input, right? X is your input, and oh wait, here I always don't know, like I can here to, no I cannot. So it's the input, and then like F here itself is some kind of model, and this model is parameterized by this weight parameter W here. So you can think of like if I adjust this W, I just have different models here. So this F is supposed to be rather flexible. We just can vary, supposingly, this is able to model anything, everything for every kind of X. For example, this X is just an image here. So, so for this input this image X here, so I should speed, as I say, speed out that label, that whether it's a cat, whether it's dog or something like that label there. And what I'm going to do is I will just adjust this weight, and hopefully this model is complex enough that I will able to find a good set of W, a good W, such that this is able to kind of like output the appropriate label here. So that's, as I mentioned, like so these features like can be the sieve and so on and so forth. So this is a kind of very dumbed down example here. So I have an image only have 4 pixels here, so I can vectorize that, and I have a model here. It's just a linear model, so I have a kind of like a can multiply by this matrix. You can think of like this is a this kind of like vectorized 2 by 2 images are multiplied by this weight matrix. So the first column, or sorry, the first row here will correspond to weight for cat. So the second row will be correspond to weight for dog, and so on. Dog, and then this is for sheep. And I can also add some bias here. So at the end here, so then the idea is here, if I have the this, for example, here like if the score is bigger, then I would say it's more likely is that object here. So in this case, this is not classified very well. This model is not a very good model. That like okay, originally this is a cat, but it's kind of classified into a dog. So we want to adjust this weight then like WMP such that like I want to make, for example, if this is a cat image now, I want to make this cat score to goes up, and for other scores to go down, goes down, go down. Yeah, and so and we still have this model here. Then as you can see, like what we need to do is like we when we want to kind of like build a supervised learning model, of course, as we already done, like we need to first define the model, determine what model we want to use. For example, like we use this like linear model in the previous example. Then we need to collect this data, right? So we have like many data in this sense, and maybe n data here, n can be 100,000, like 10,000, and so on, maybe more. And so this data will be just a pair for each of the input. We want to know the true labels there. So, and then when we have to collect data, now what we want to train the model is just we're trying to solve a optimization problem, right? So in the sense that like we want to have the for the model, so basically we have the W here. We want to find the W such that when I input some training data for a particular training data, for example xi here, I want to make sure that the output there, like this in this case, fxiw, will be close to my true output here, right? Close to my yi here. So this L is just a so-called loss function. So it's going to kind of compare the difference between these two. So in the sense we want this to be as small as possible, right? So this kind of totally intuitive, right? Totally makes sense. So and typically we will add a so-called this regularization term as well. This thing, I don't know. At least most of the time it will help. So this thing is like trying to make your model don't go wild in the sense like you can, if you don't have this regularization, using the classic ideas that you may overfit your model, something like you have the model is just doing very well for your training data but doing poorly for your actual testing data. So am I clear myself, like basically? So remember that like we are trying to solve this optimization problem. This is your training data you see, but for machine learning or for whatever deep learning, for all this problem, the most important kind of like metric is like generalization, is the testing data, right? So I don't care about the training error, honestly. So I can have like poor training error, but I care about the testing, right? I see all these like images during training, but what I care is like what for the future image I see during testing. I want it to be able to kind of like classify it correctly. So therefore, like if I just train the model in the sense like so-called overfitting, that it do extremely well for this training data, but it did poorly for the testing data. It is no good to us. So and this regularization term is supposed to kind of like mitigate this problem there. And this regularizer, as I said, is typically is trying to penalize complex model. So when the model is overly complex, it will try to overfit the data, so try to fit the training data as much as possible. And when we try to penalize this model to be not as complex, that's likely that like it won't try to overfit the model. But as I said, like there's some recent research that I'm not sure I like to talk about that. It's like still pretty recent, like last couple 1 2 years, and that's kind of like imply that like we may not even need this regularization terms if our model is complex enough. But yeah, I don't know, like, but at least for the classic machine learning, we know for, let's say, like 2 3 years ago, this definitely is like the I will say, like, if you ask many people, still like this is a kind of like common knowledge to everyone working in this area. So, and by the way, no problem so far. Right? If you have any problem, just interrupt me. Again, let me just check the chart every while. Uh, so, and let's look at an example like doing linear regression. The so-called linear regression, actually more precisely here, is like which regression if we use a regularizer as well. More precisely, is if I use a L2 regularizer, what's that? L2 norm regularizer, and and the linear regression problem is like it's just I have a model. It's just linear. It's like this, and I'm considering a problem trying to fit my it's a continuous problem. I should start with saying that it's a continuous problem. So you can think of like a classic example is like maybe I want to predict the price of a house. So I have features here x here, maybe like the size of the house, uh, number of square feet, like the locations, uh, I mean the number of stories, and uh, like the building materials and so forth. And then like with that, we can create this feature, and I can use a linear regression model, which is just like I multiply this feature. This feature is now a vector, and I multiply by here is I just if I'm just predicting the price is just one value, so then it will be just multiplied by another vector in the product and another vector. Then I will estimate the price. So the loss in this case will be a simple Euclidean distance, right? So if my output is like more than one dimensional, maybe multi-dimensionals, maybe I want to predict uh, 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 maybe not predicting the price of a house, but I for something of predicting the weight and height of someone like a year from now or something like that. So based on like his body kind of features at this moment. Of course, I assume that this person and maybe is a child, and like otherwise predicting height doesn't mean much. So maybe I then it would be like a two-dimensional vectors, like 2D vectors. So I can have a loss would be like a two kind of computing the second norm of that two. I mean the Euclidean distance of this prediction from your estimate basically. And I'm not sure. Do I need to like specify better like this kind of notations? Like, so what I mean, this one will be like y square. Maybe I just write it out anyway. Something like that, right? So if this is a length n vectors here, so it'd be something like that. Yeah. And then I regularizer. We can use this regularizer. Like this have a fancy name known as the Frobenius norm, but it's actually just like it's is the sum of square of all the elements in the matrix. So more precise, if this matrix is m by m, then like this Frobenius norm is really just equal to w and m something like that. So then the learning model will be the whole thing is be just like that way as we see earlier. So the loss is basically like this, right? So remember the last previous slide we have this one is a L Y hat and Y something like that, right? So actually more precise here should be Y something like that. I think this probably missing an I here. Yeah, I should say YI. Okay. And I have this one will be the estimate will be YI hat here, and then this is like the YI. So I look at the losses just the Euclidean distance as I already mentioned. So and add the regularizer like this. And then in this case, I just try to minimize this W. So as you can see, actually for this problem, you can solve this in closed form, but we are not going to solve it here. So but instead, I also look at like the other problem, like so for the problem I just mentioned, this is a regression problem, like trying to predict a continuous value. So let's say if we go back to a classification problem, like want to classify this is whether it's a cat or dog and so on, then in this case, I will instead of using a actually, I haven't ended yet. This is a for the I'm thinking whether I want to follow these slides here or I want to just. But okay, anyway, maybe I follow the slides here. Maybe I shouldn't have these slides here. Like, it kind of like. So if I follow the slides, like what the slide here I want to say is like, okay, we have this linear regression model like we just mentioned earlier. So if we want to create a more complex model, say like this linear model is not sufficient. So what we can do is like, how about we impose multiple layer, so we can have like maybe like 2W here, like this is 1W for the first I mean multiple layer, then in the sense I first have this x here, right, x multiplied by W1, then I have some intermediate, maybe I call it C, and then I multiply by W2 again, I have Y. So instead of one layer X multiply W1 and then get Y, I go for two layers. But of course, if you look at this more carefully, this is of course pretty silly, because if I do that, like I can have this is just this combined is just W2 times W1 is still just one matrix, right? So I don't have any gain basically. So what I mean is like this sense of like having two layers is meaningless, but instead like I can have a more representative model if I introduce some nonlinearity here. So let's say in the middle here, x and c here up, rather than I just multiply by W1 here, let's say I still have c is equal to x, W1 multiplied by x, but maybe I have like c tutor is equal to some nonlinear function of c. So some nonlinear function, like very classic one, can be like this kind of sigmoid function. I apply this nonlinear function. I have this c tutor instead, and c tutor will be kind of like plugged into the next layer, and I have like c tutor. I have now this time y will be equal to W2 multiplied by C tutor instead. And then like I can have another activation, so another nonlinear layer here, let's say sigma y, that is basically y tutor is sigma y, something like that. Then we will have a more representative model, a more powerful model. So that's this precisely these two slides trying to to mention that. So instead of like just having like these two measures simply multiplied together, so your neural network is like, when we say neural network, it's nothing. It's just a linear model followed by a kind of nonlinear activation function. So and that's what why people call it neural network. So maybe I should step back a little bit to say why this kind of neural network, because like people consider each of these pieces is like known as a neuron. So it's like this artificial neuron. So think of like in comparison, if you have, I don't know whether I have slides like that in the future. So if I have them, maybe I use those slides. I forgot because I have several set of slides like this, so I don't even remember like what I have here. Yeah, so I don't actually. Uh, so anyway, then maybe I just go back and uh, hand draw or something. Um, so we were here, I think. So what I mean is like you think of like what actually I should get used to using this, right? I can, yeah, this is much easier. So uh, I what I mean is like you have this so-called artificial neuron. Is if you think of humans neuron, it's like you have this I don't know how to draw it without a picture. Um, so we have this neuron is oh, I don't remember. So I have probably something like that, and you have one end is kind of like getting chemical from these other neurons, right? So you can think of like neurons is sending output to the next neurons, and the neurons say when you have like enough activation here, it will fire, right? So therefore, like you can think of this is like uh, when you collect inputs here, it's like a weighted sum of the previous input. So in terms of this particular neurons here, if you think of this one here, it's just taking input, a weighted input from all the neurons, or like for the connecting neuron from P, from the other side, and then wow, this is a very, let's see how do I, huh, this is still so stupid. I cannot find eraser there. So and then like when we have like enough stimulation, then it will fire, right? So if fire will fire kind of like in a non-linear manner, right? It will not simply like sum over all these values. So actually in reality, like this firing is like having kind of like some kind of time code. It's like something like if you activate, if have like some kind of codes coming in, like it's kind of fire like rapidly, something like that. But we can model that like with just a intensity, but the intensity would be something like um, capped by some value. So therefore, like when people first starting to think about neural network, design neural network, they use model like this sigmoid function. Actually, I didn't draw the sigmoid function correctly like previously. That one was a tangent I'm drawing, I think. So the sigmoid function will be like that way. So when your value, when the input is sufficiently large, you will cap to 1, something like. When it's kind of small, it basically is 0, like kind of very negative. Um, and because each of these independent units is kind of like imitate like a artificial neuron, so therefore when you combine all of this together, you call it a neural network. Um, and typically you will kind of like uh, organize your neural networks into layers. So you have like first input layer here, and then like typically you have some hidden layers or one or more hidden layers, and then you connect to like a output layer. So this is like the most basic neural network model. So it's like kind of people don't use sometimes refer this as a fully connected neural network because like, each of them is connected to everyone else. So you're just trying to train this W here to such that like you will for a given input you will have your desired output here. So then this slide is just saying what we mentioned earlier that like now using neural network you can do something more end to end. Previously, we are trying to like hand engineers this kind of image feature, but now instead like we just take this as a into our model as well. So we just try to build a multi-layer neural networks like this one, like many layers, and then just train end to end. Hopefully, like the earlier layers will be able to capture the features of the image, and then the later layer will be doing the classification. Um, Again, like this kind of ideas people keep changing. Like, this is like what people was thinking, or like I guess many people still think like that. But some of the people, for example, listen to a very influential like kind of neural network researcher like Goodfellow, like he created GANs, like invented GANs. He didn't agree that like he doesn't think that like we should think like that anymore. But anyway, like so any many people have different opinion, but um I guess like still like you just as an approximation of thinking like about like what neural networks is like, I guess still a pretty good way to think about that. So and that's what's my time doing. Okay, okay. So I guess yeah, I guess that's fine. I can talk about gradient descent maybe like talk about backpropagation next time. So um I mean like we have the problem. We come back with the machine learning problem again. So remember problems like this is like very universal. Basically, if you look at all the machine learning is doing, at least like all supervised learning doing, is just like trying to solve problem like this. Again, like you're just trying to fit your model. The model basically will be parameterized by some weight W here, and then you want to fit the model such that your expected output or your expected output is basically this yi here is close to your model output now, like with the current model what's the current output now, and this closeness will be measured by some kind of loss function, and we also like typically add a localization term like this to try to um, make sure the model is not overfit, and then the problem become an optimization problem, right? We just want to now trying to find W such that this thing is like minimized. Um, so I mean, you can. I mean, this is some silly idea. I'm not even want to mention that. If you try to solve an optimization problem like this, uh, of course, you can blindly do that. Like for example, like you can just arbitrarily plug in some W and see like if you can get reach the minimum. But you are looking into a very high dimensional problem. Typically, your W for neural network models, it can easily go to a million parameters. So you need to like randomly select this million parameters, such as you want to reach a minimum. This is basically impossible. Uh, and you that's basically random search here. Some for some cases you are able to find the closed form solution. For example, like when we mentioned the regression problem with the Euclidean with the Frobenius norm as the regularizer. Actually, this is it can be solved like in closed form. It's not difficult to solve at all. So for those particular, it's very few, basically very few models can be solved like that. For most problem, like what we can do the best way is just trying to do gradient descent. So steepest descent. You think of like you're just trying to optimize this. What we're going to do is we try to compute the gradient. So if you guys remember like what gradient is like from calculus class, so you have this scalar function. Basically, you can think of this. Now the whole things I can call okay, it's already called GW here, right? And it's basically it's a scalar function but have multivariate argument. So so like this, if in 2D case, it's like in the discrete things here, and the gradient, if you remember what gradient mean, the gradient is like if I have a vector, or if I GW, W is like n-dimensional, so something like W1 up to Wn here. So then the gradient usually represent as like that. Will be, maybe I put a W here. Let's just specify this. The variable is W. With something like the partial derivative, partial W1 to partial G, partial Wn, something like that. Actually, like for the gradient, it's only defined for 2D, so it's thinking vector. But if you heard of like low lateral packages, like heard of like something like TensorFlow, you kind of like wonder why they call it tensor, because when you play with that, like many of these data structures are multidimensional arrays. So you can extend the idea of gradient like into like higher dimension. For example, if I have my W is a matrix, for example, a 2x3 matrix like that. I hate this. Maybe I just should use like. So maybe I have my W is a 2x3 matrix, right? I can write W11, W12, W13, W21, W22, W23. I have GW again, right? G is a scalar function. I can look at maybe I won't use the gradient Laplace. I think this is called Laplace in latest. I don't know why. So partial P, partial W. Maybe I write like this. So this will be. By the way, what's the dimension of this guy supposed to be? Can anyone answer me? Like just near the end now.
2 by 2.
Wait. W is this dimension. What's the dimension of like these things supposed to be a reasonable dimension for this guy? So think of like an analogy of like gradient in 2D. So if I have like W, and now maybe I don't call it W, I have a X is like a 3 by 1 is a vector like x1, x2, x3. Then you have the gradient of G x will be like partial G, partial x1, partial G, partial x2, partial G. Oh, this is hard to write. Partial x2, partial G, partial x3, right? So this is also the dimension is like 3 by 1. So what I want to say is like actually this gradient like things, the dimension, if your G is a scalar here, this one will have the same dimension as this guy. Same dimension as W here, because this one should really define as a parcel G tuple W 1 parcel G parcel W 1 2 parcel G parcel W 1 3 parcel G parcel W 2 1 parcel G. Something like that, right? So do you guys all agree with that? So I can even have W is like not even 2-dimension. I not even matrix. I can have like a 3D structure where I can have like W is actually, I don't know, I have like IJK index, basically W1 IJK, and then like maybe like each of the dimension is like 2 times 2 times 3, let's say. Then my parcel G parcel W should also have the same dimension as this guy. So in this case also will be a 3-dimensional structure with like dimension 2 times 2 2 by 2 by 3. So now I guess near the end maybe I just give one more kind of like questions for you guys to think of, like how about if my G is not 1-dimensional? Maybe my G is like have structure like this. G is like, maybe my G is also a vector, so I have G W. Now let's say my W is like this guy again, like it's just 2 by 3. Maybe my G, I don't even know whether I should write. Maybe my G is like that, G1W. Maybe I don't write the bar because it's not really a vector. G2W. Now what will be this like partial derivative? What's the dimension of this partial derivative? Anyone? I wonder Iswa is here because she is always will help. Maybe she is not here today. Yeah. So
I'm here. I'm just trying to like process something because I am. Are you following up?
Okay. Okay, it's okay. Do you follow this one? Like, should I repeat my question or like?
Oh yeah, I would like to hear that
Okay,
again.
okay. Let me repeat the question again. So, I have consider like I have G is like a function of this W. W is like a 2 by 3 matrix here, 2 by 3 matrix here. And G itself is like a two-dimensional. So therefore, like G is like something like G1W, G2W. So now, my question is like, a appropriate definition is this partial derivative. Oh, no, I shouldn't say partial, but the gradient of G with respect to W. What's the dimension supposed to be?
G is with W. I'd say 2 by 3. Also. No.
Close. You can think like, if only for G1 itself, like that would be a 2 by 3 already. So because you have another T2, so there's a 2 by 3 by 2 something, or 2 by 2 by 3 something like that.
I think we'll have 2 by 3 for like G1 and 2 by 3
yes.
for G2.
So that if you think of that, this is like 2 layers now. So it's like yeah, I don't know how to draw. Yeah, this is kind of parcel G1, parcel W11, parcel G1, parcel W12, parcel G1, parcel W13, parcel G1, parcel W21, parcel G1, parcel W22, parcel G1, parcel W23. So I have one layer like that. Then I have another layer, something like the same thing, but it's like partial G2. Um, so I guess I'm near the end, but yeah, I think I already like. Okay, I guess I will go back, come back next time. But today is what, Tuesday? Yeah, I'll come back Thursday then. So I think like this is actually um I yeah, I think this is actually important. Like when you have all this sort out, you find that like uh backpropagation is really obvious. So even actually even now it's obvious, but like it's even more obvious. So we'll talk more about that later on. Okay, on Thursday.